Hello everyone, my name is Grant Lewis and I'm an intern at Inano. I recently graduated this past spring of 2024 with my bachelor's in electrical engineering, and I will be starting my master's in electrical and computer engineering this fall. This past summer I was able to serve as an intern at Inano, and I am here in our lab now. I was able to help with projects ranging from measuring physical devices to simulating and designing schematics for the project that we are working on, which I'll be going into more detail later. Momentarily, I will be giving a brief tour of this lab, but first I would like to thank several individuals. Firstly, I would like to thank Professor Saif Islam. He is the PI for Integrated Nano Devices and Nanosystems Research Lab, or Inano, and it's thanks to him that I found this internship, and also thanks to him that I was able to conduct research as an undergrad before I even joined this internship. Secondly, I would like to thank Amita Rawat. She is the postdoc at Inano, and she patiently guided me through how to use Cadence Virtuoso along with many other tools that I used this summer. I would also like to thank Asan Ahmed. He guided me through the lab safety training and also taught me many other things that I know about how to behave in the lab or how to use things in the lab. I would also like to thank Lisa McPhillips. It's thanks to her that I know how to use also a lot of the tools in the lab, and she allowed me to shadow her on multiple occasions to watch what she's researching and learn from her. Lastly, I would like to thank Samir Ali. We worked together. He is a community college student from Delta College, and we were partnered together for this internship, and almost everything that I go over in this presentation, he had some part in, which he will go over in his own presentation. But huge thank you to him. I had so much fun working with him, and I hope you go watch his presentation as well. Now, let's get started with a brief tour of the lab. Firstly, here is the probe station. This is where we place our chips to probe and measure the devices, and we can look at it through the microscope to see what we're doing. This here is one of our chips. You can see all those little circles are individual devices that we might probe and measure at this probe station. Coming over here, we have the NKT laser. This can output many different wavelengths so that we can see the response of a device to that wavelength. It's not a super powerful laser, but just to be safe, we wear these green glasses which protect us from the laser. Now I'll be moving on to my slides part of the presentation. Thank you, PassMe, for that wonderful tour of the lab. Let's get started now with the slides. Firstly, here I want to show you in a little bit more detail the semiconductor chip. This was one of the chips that I was able to take measurements of, and so each little circle is an individual device that we might probe and take measurements of under different conditions just to see how it behaves. Here are some of the individual devices. First here we have very small devices, and we can see the probe tips. So we probe this device so that we could take measurements of it. Right here we have a probed 500 micrometer avalanche photodiode, or APD, and this is a similar APD but unprobed. Now back to this picture, you can see the two probe tips, but right here, this little shadow, that is the shadow of the fiber optic, which is connected to the laser. This is the laser that we have. I briefly showed it in the tour, but you can see that it outputs a wide variety of wavelengths, and so each one of those wavelengths we can shine on our device and see how that device behaves under those wavelengths and conditions. And so when we do that, we would usually do it in the dark, so only that specific wavelength is shining on the device. And so this is a very helpful machine, and again, we wear goggles when using that machine. This is the results of using the laser and measuring the photodiodes. So this here is an IV curve, which is current versus voltage. And so we can see the dark current here, which is it in the dark. And then these are it illuminated with different wavelengths coming from that laser. This is the EQE graph, or external quantum efficiency, and this is the gain. Something else that I was able to do in the lab is take CV measurements, or capacitance voltage. And so this essentially is another way of measuring the device and just another way of measuring how it behaves under different conditions and things like that. Now, going back to the very start of my internship, I started research with a D flip-flop. This is actually a D latch, and so we can see the logic here. I also researched some other flip-flops, and this was to just help me get started researching the D flip-flop, and then I later was able to create a schematic and simulate it in Cadence Virtuoso. I'll get more into that later. Before I get into Cadence Virtuoso, I want to talk about the big picture of what we were working on this summer. This is the main device that we're working on. It is an avalanche photodiode array. You have 16 individual avalanche photodiodes. You have this row select here, these 4-bit ADCs, or analog digital converters, and this output buffer. So myself and the other interns were mainly working on this control block right here. This control block generates the clock signal that tells the ADC when to run. It also tells the row select which row it is currently needing to select, and so that's another signal. And then it also will be generating a pulse that simulates like a laser pulse. So when simulating the D latch in Cadence Virtuoso, I first generated this level triggered D flip-flop, or D latch, and so this essentially will update D whenever the clock is high. So we can see here D and clock are both high, so Q is high, and then clock is high right here, and D is low, so it updates to low. And then right here we have D is high, clock is high, so it updates to high, and then D goes to low, and clock is still high, so it again goes to low. That makes it a D latch rather than a D flip-flop. This is a D flip-flop. This will update whenever the clock rises from 0 to 1. And so we can see that in this one, if we have an update right here with this falling edge, that doesn't update because the clock is already high and isn't rising. We get this update right here because the clock rose while it was high. And this is the schematic. It's essentially two D latches put together. Now, with our inverters, this is a very critical component. It's in almost everything that we did. Very simple device, but still very crucial. Right here, we can see we're testing with a load capacitance of about 400 attofarads, and these are the results that we got from this device. And we adjusted the PFET width to 155 nanometers while keeping the NFET width at 80 nanometers. The reason that we did this is so that we get a symmetric rise time and fall time. And so basically we have an input signal, a simulated input signal right here at the in, and then we read what comes out. And so briefly, how this device works is that when you have a high input, the ground is low, the input is high, and VDD is high. And so this device is off, and this device switches to on, and so the output reads as low when the input is high. And then similarly, when the input is low and ground is low, this device turns off, this device turns on, and VDD flows to out. So one of the things that we did with this inverter is build a ring oscillator. Here is the ring oscillator. We tested it with 3, 5, and 7 inverters, and basically you put the inverters in series, and then those inverters generate a clock-like signal. And during this designing and testing, we also found that SLVT transistors outperformed LVT transistors, which we were previously using, and made a faster ring oscillator and a sharper response. So using the ring oscillator, we began testing what kind of signals we could generate with that. And so I experimented with different variations and even generated some asymmetrical waves, which we can see down here. However, in this phase of testing and design, I forgot to remove the load capacitors which are supposed to be used only for testing, but I was leaving them in the actual circuit, which was giving me bad results. And so this is the schematic where I have a ring oscillator, and variations of buffers and stuff. So I began to make improvements on this, where I removed the capacitors, and from almost all inverters, but not quite all inverters, I was still leaving them in the ring oscillator to slow down my signal, because I was aiming for a 500 picosecond period, and so it generated approximately that, but we can see this waveform isn't completely symmetrical, so it still needs improvement. I was also able to generate a decent asymmetrical signal, but in this specific image, we can see that this isn't perfect, because we should also be getting a pulse in the middle of this pulse and this pulse. But because of the clock not being symmetric, we're not getting that. So I detoured to make further improvements on the ring oscillator to improve that not symmetrical clock, and I removed all the capacitors and adjusted the ring oscillators to create a 500 picosecond period for the signals that they output. And so I did 3 inverters in series, 5 inverters in series, and 7 inverters in series. And the gate length for each of those can be seen right here: 408, 295, and 238 nanometers. And so essentially what that does is that slows down the N and the PMOS so that we can get that 500 picosecond period. And I adjusted those to get really close to 500 picoseconds. Some of them were like 498, some of them were like 502, but it's really close to that 500 picosecond ballpark. And using these new ring oscillators, I fixed up the signal and was able to generate a much nicer asymmetric wave. We have a nice 500 picosecond period on the clock. A0 and A1, which are what goes into the row select, have a nice 1 nanosecond and 2 nanosecond period, and V-laser is asymmetric with a 1 nanosecond period, and we're not like missing out on any pulses. It is adjustable just by adjusting the inverters for the NMOS and PMOS. And so this is basically the final design, and we're currently working on integrating this with everyone else's design. I hope you enjoyed this presentation, and thank you so much for watching.